In this video, we're going to look at another global analysis called Liveness Analysis. So in the past several videos, we've looked at a procedure for globally propagating constants through a control flow graph. And here's one of the control flow graphs we've been looking at, and recall that this algorithm that we discussed would be sufficient to show that we could replace this use of x here by the constant 3. And once we do that, this assignment to x might no longer be useful. It might not be used anywhere, and so we could potentially delete this statement from the program, and that would be a real optimization, an important optimization to do. However, we can only do that if x is not used elsewhere in the program. So let's be a little more careful about what we mean by saying that x is not used. So down here is a use of x, a reference to x in a statement. And clearly, this particular reference to x is picking up the value that's defined by this write to x here. So we say that the write of x here is live. This one is live. Okay? And what that means is that the value may be used in the future. So live equals may be used in the future. Okay? So the value written to x at this line of code may be used by some subsequent instruction. And here it's not just that it may be used, it's actually guaranteed to be used because there's only one path, and that one path has a reference to x on it before there's another assignment to x. Okay, so this particular value of x as written here is guaranteed to be used, but in general we don't require that. We just mean there has to be a possibility that it will be used. Now in contrast, let's take a look at this other statement in this example. Here we assign x the value 3, but this assignment to x, this value of x, is never used. This one is dead. All right? Because the value 3 here is overwritten by the value 4 before there's any use of the variable x. Okay, so this particular write to x will never see the light of day. It'll never get used by any part of the program, and we say that it is dead. So to summarize, a variable x is live at a statement s if there exists some statement that uses x, okay, so some other statement s prime that uses x, and there is a path from s to s prime, and there's no intervening assignment on that path to x. All right, so there needs to be an assignment to x at some statement s. There is some path through the program that reaches a read of x at some statement s prime, and along that path there is no write to x. Okay? And if this situation arises, then we say that this value written in this first statement s is live. Now, if a value is not live, then it is dead, and a statement that assigns to x is going to be dead code if x is dead after the assignment. So if we know that immediately after the assignment, meaning immediately after this assignment to x, there is no possibility that a value of x will be used in the future, well then the assignment was useless and the entire statement can be removed. All right, so dead statements can be deleted from the program, but notice that in order to do that, we have to have the liveness information. We need to know whether x is dead at this point. So once again, what we want to do is to have global information about the control flow graph. In this case, the property is whether x will be used in the future. We want to make that information local to a specific point in the program so we can make a local optimization decision. All right, and just like for constant propagation, we're going to define an algorithm for performing liveness analysis. And it's going to follow the same framework. We're going to express liveness in terms of information transferred between adjacent statements, just as we did for copy or constant propagation. And it's going to turn out that liveness is actually quite a bit simpler, or somewhat simpler than constant propagation, since it's just a Boolean property. It's either true or false. All right, so let's take a look at some of the rules for liveness. So here, we're defining what it means for x to be live at this point here. So immediately after p is x live, and it's going to be live. Remember what the intuition is. The intuition is that the variable x is live right after p if the value of x is used on some path, on one of the paths that begin at p. All right? And so in order to know whether it's live, we're going to take the liveness information at each of the input points. So that would be here, 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 and here. So each of the successor statements after P. And we're going to ask, is X live at any of those points? So it's just a big OR over the liveness of X at all of the successors of P. And that's the liveness of X at the out of P. Next, let's consider the effect of individual statements on the liveness of X. So the first rule is that if we have a statement and it reads the value of X, okay, so here we have an assignment statement, and on the right-hand side it refers to X, so it's reading X, then X is live before that statement. Clearly, X is just about to be used on the in of this statement, and so X is live at that point. All right, so if a statement reads the value of X, then the in of that statement, X is true. The liveness of X is true. A second case is when a statement writes the value of X, so here we have an assignment to X, and the rest of the statement does not refer to X, does not read the value of X, so there's no X in E. Okay? So in this situation, X is not live before the statement. X is not live, or we could say that X is dead before the statement. And why is that? Well, we're overriding the value of X, so whatever value X had before this statement is never going to be read, okay, because the E here, the right-hand side of the assignment, doesn't refer to X. And so immediately before the statement, the current value of X is never going to be used in the future, and so X is dead at that point. And finally, the last case is, what if we have a statement that does not refer to X? Okay, so it neither reads nor writes X. Well, then whatever the liveness is of X after the statement, it has the same liveness before the statement. So if X is live here, then X will be live here. Okay, and similarly, if X is dead after the statement, then X must be dead before the statement. And that's because if X is not used in the future after the statement S, then it still won't be used in the future before the statement S, since the statement S neither reads nor writes X. So those are the only 4 rules, and now we can give the algorithm. So initially, we let the liveness information for X be false at all program points, and then we repeat the following until all the statements satisfy the rules 1 through 4. And just as it's the same algorithm that we used for constant propagation. We pick some statement where the information is inconsistent, and then update the information at that statement with the appropriate rule. So let's do a simple example, something with a loop. So let's begin, say, by initializing X to 0. And then what should our loop body do? Well, we can check whether X is equal to 10. And if it is, we'll exit the loop. And let's assume that X is dead on exit, so X is not referred to outside of the loop. And otherwise, if X is not 10, then we will increment X and we'll branch back to the top of the loop. So this is a very, very silly little program. It just counts to 10 and exits. But let's do the liveness analysis to see where X is live. Okay, so since X is dead here on exit, it's clearly going to be dead on the out of this conditional on this branch. Okay, so I should say that X is not live. So we're using Booleans here, so X's liveness would be false. And we're assuming that X is also not live every place else initially. Okay, and so there's a program point in there also where the liveness of X is false. Okay, so now let's propagate the information. Well, so here we have a read of X, and let me switch colors here. So here we have a read of X. So in fact, the information is inconsistent here because right before this statement, since we have a read of X, X must be live. So in fact, X is live at this point. Now notice that this statement both reads and writes X. Okay, but the rule that says X is live before, when we do a read, takes priority here because the read happens before the write. So we'll read the old value of X before we write the new value of X. Okay, so the old value of X does get used, and that's why X is live immediately before this statement. All right, so then here's another read of X. Okay, so on the so at the point immediately before this one, I left out one program point here. X is also live. Okay, and then following edges backwards, well, that means X is going to be live on the back edge of the loop, and it's also going to be live going into the initialization block. All right. Now we come back around here and we see that we're done because X is already known to be live within the loop body. And now X is also live here. And then the question is, what about this point on the at the entrance to the control flow graph? Well, there's a write of X and with no read of X on the right-hand side. So in fact, X is not live on entry to this control flow graph. So in fact, X is dead at this point. So whatever value X has, when we enter the control flow graph, it will never be used in the future. All right, and so that is the correct liveness information for every program point in this example. Now, another thing you can see from our little example is that the values change from false to true, but not the other way around. So every value starts at false, and it can change at most once to say that the value is actually live, the property becomes true, and then it won't ever change back to false again. So going back to orderings, we only have two values in this analysis, false and true, and the ordering is that false is less than true. Okay, and so everything starts at the lowest possible element of the ordering, and they only move up, and so they can be promoted to true, but not vice versa. And so since each value can only change once, termination is guaranteed. Eventually, we're guaranteed to have consistent information throughout the control flow graph, and the analysis will terminate. To wrap up and summarize our discussion of the global analysis of control flow graphs, we've talked about two kinds of analysis in the past several videos. Constant propagation is what is called a forwards analysis because information is pushed from the inputs to the outputs. So if you think about a control flow graph, what happens in control flow analysis is that information flows in this direction. It flows in the same direction as computation. If I have a constant up here, X is assigned a constant down here, and X is used later on, then that constant will flow forward to the uses. Okay, so information flows in the same direction as computation. Liveness, on the other hand, is a backwards analysis. Information is pushed from outputs back towards inputs. So here, in this example, and let me change colors, here we see that X is live before this statement, and that liveness gets propagated in the other direction. It gets propagated against the control, against the flow of execution backwards towards the beginning of the program. So there are many other kinds of global flow analysis in the literature. The constant propagation analysis and the liveness analysis are two of the most important. There's a number of others that are also very important and many, many more that people have investigated. Almost all of these analyses can be classified as either forward or backward. There are some analyses and some important ones that are neither forward nor backward. Then information is basically pushed in both directions. And the other thing is that almost all the analyses in the literature that do global flow analysis anyway also follow this methodology of local rules that relate information between adjacent program points. So that's really the local rules part that's important. So we break down the complicated problem of analyzing an entire control flow graph into a collection of rules that only do propagate information very, very locally.